Alright, so let's do another force decomposition problem. I've got this vector f. I want to split it into pieces that are in the e hat 1 and e hat 2 direction as defined in this picture right here. So I'm going to go to my recipe. I'm going to draw a force triangle. So the original vector f, that's the hypotenuse of my triangle. Then the other two sides are sides that are parallel to the e hat 1 and e hat 2 direction. They add up to f. So in particular, I start at the base of f. I move in the e hat 1 direction, right, that much, and then I move in the e hat 2 direction, or in this case the minus e hat 2 direction, but in the direction parallel to the e hat 2 vector, like so. And since e hat 1 and e hat 2 are perpendicular to each other, this angle right there has to be 90 degrees. So there's my vector triangle, and I write it in a way so that these two sides right here are arranged tip to tail, so these two vectors add up to the f. Now what I want to do is I want to find the lengths of these two sides. And to do that, I'll have to do a little bit of geometry. So first I'm going to notice the thing that's given to me, this angle theta right there. What is that? That's the angle of the e hat 2 direction relative to horizontal. So here's a horizontal, and this piece of my triangle, that's parallel to the e hat 2 direction. So that angle right there, that is theta. Right now, this angle right here, theta, is not an interior angle of my triangle, so it's kind of hard to work with that one. So let me go a little bit farther. So if this angle is theta right there, then this angle inside here, that must be 90 degrees minus theta, right? Because that whole angle from horizontal to vertical, that's 90 degrees, so there's 90 degrees minus theta. And just a little bit of geometry, all right, over here on the side. Let's suppose we've got some sort of triangle. And let's say for this triangle, I'm going to call this angle alpha, and I'll call this angle beta right there. And let's say this is a right triangle, so that's 90 degrees. If I have a triangle, then alpha plus beta plus 90 degrees, those are my interior angles, those have to add up to 180 degrees. Like so, bring the 90 to the other side. That means alpha plus beta for my right triangle have to add up to 90 degrees. Right, so if this angle right here, where are we, right here, is 90 degrees minus theta, then this angle right here has to be theta if these two angles are going to add up to 90 degrees. So therefore, I've identified that angle, that interior angle of my triangle, as theta right down here. So now what I do is use a little bit of trigonometry. So in the e hat 1 direction, which one is this? This is the e hat 1 component of my force F. That's the side adjacent to theta in my right triangle, so that's why I have a cosine theta right there, f cosine theta. And this side over here in the e hat 2 direction, that's the opposite side. It's opposite of the angle theta. So hence I have the f times sine theta. Now let's make sure I get the signs, S-I-G-N-S, of the problem right as well. So this piece in the e hat 1 direction, right, it starts down here and moves upward and to the left. Notice my e hat 1 direction goes upward and to the left too. So therefore that makes sense that we've got this component's in the positive e hat 1 direction. Whereas this piece, the e hat 2 component, it's going up and to the right, whereas e hat 2 basis vector goes down and to the left. So these are opposite directions. So that's why I have this piece in the minus e hat 2 direction. And that explains the whole thing. So let's put a box around it. So there's my answer.